Hey calculus students, this is some more problems from chapter 4. This is sections 4.3 and I don't know why I write 4.2 there. This is 4.4. So greatest hits, chapter 4, volume 2. I picked these problems because I thought they were good ones for you to have in video form. So here we go. Number 17 from section 4.3. We are taking the derivative of y equals e to the x tangent x. So the derivative of e to the whatever is e to the whatever. But the way the chain rule works in this kind of problem, the whatever here, the derivative of e to the whatever is e to the whatever, but the whatever here wasn't an x, so I need to multiply by the derivative of what's inside, and the what's inside here is the what's up there. So the derivative of what's up there, let's see, that's a product, so x tangent x. The derivative of x, the derivative of the first is 1 times the second plus the first times the derivative of the second. So the chain rule feels a little different in these e to the whatever problems because the what's inside is really the what's up there. Right, that is the what's inside. Derivative of e to the whatever is e to the whatever times the derivative of whatever. Number 21. Taking the derivative here of y equals the natural log of 1 minus minus 1 minus x times e to the negative x. Alright, so let's see. The derivative of natural log of whatever is 1 over whatever. Times the derivative of what's inside. The derivative of what's inside here, derivative of 1 is 0. And then I'm going to put the negative sign on the outside here. And then the derivative of this is a product, x times e to the negative x. So I took care of the negative sign, I put that on the outside. My product rule here now, derivative of the first, derivative of x is 1 times e to the x, e to the negative x, sorry, plus the first times the derivative of the second. The derivative of e to the negative x is e to the negative x times the derivative of what's up there, which is negative 1. There's a little bit of simplifying you could do there, I suppose, but not a huge amount to be gained by simplifying that. You could distribute this negative sign, that would make this minus and cancel out that negative 1, but I'm going to leave it like that, and you can simplify that or not. Number 25, we've got f of x is equal to pi to the sine x. I'm going to rewrite that as y equals instead of f of x notation, just because I think that makes it a little bit easier to do in logarithmic differentiation. So the directions here say use formula 7 and then by logarithmic differentiation. So I'm going to skip the formula 7 part and I'm just going to go ahead and do logarithmic differentiation here. So I'm going to take the natural log of both sides of this. So let's see. The natural log of pi to the sine x is the natural log of pi to the sine x. Now the reason we do logarithmic differentiation is because we have a logarithm rule that says whatever that exponent is, you can bring that to the outside here. So I can rewrite that like that. And now take the derivative. So the derivative of natural log y, derivative of natural log of anything is 1 over that thing, times the derivative of what's inside. Derivative of y is dy dx. And now I have a product here. But actually this isn't really a product because natural log of pi is just a number. So the derivative of a number times sine x is just that number times the derivative of sine x. And then here, multiplying by y on both sides, I get dy dx is equal to y. I could write a y here, but y is equal to pi to the sine x times natural log of pi times cosine x. So if you're wondering what they're talking about with their formula 7, their formula 7 is just if you have a number to a power, then the derivative of that is that number to that power times the derivative of that power times the derivative of the base. If it's e to that power, then you're good, right? Because the natural log of, if this was an e, natural log of e is just 1. But if it's not 1, then you have that factor also. I think it's easier to just understand this by doing logarithmic differentiation. Then you don't have a special formula to remember. So that's what I would recommend for you there. 29. Y equals natural log of x to the tangent x power. Now, when you have this natural log of, or this something happening with x's to the something happening with x's power, then you have no choice. You must do logarithmic differentiation. There's no choice. Here we had a choice if we know that special formula, we know how to deal with this number not being e and this not being just plain old x. You could memorize that formula. Here you must do logarithmic differentiation. So that means I must take the natural log of both sides. So let's see, the natural log of this, natural log of x to the tangent x. I could write that here, but the reason that I do logarithmic differentiation is because that can bring this power now to the outside. So I'm going to do that. And that turns that into a product. Now, taking the derivative, I have not done any calculus yet. This is just taking the natural log of both sides and applying that natural log, that logarithm rule there. So now I'm going to take the derivative of both sides. So the derivative of natural log y is 1 over y times dy dx. And I have a product here. So let's see, the derivative of the first is secant squared x times the second plus the first times the derivative of the second. This is the second here. So the derivative of natural log of whatever is is 1 over whatever times the derivative of what's inside. And I've got my 1 over y here, so if I want to write this as dy dx equals something, then I multiply both sides by y. I move this to the other side, and y is equal to, naturalize my original function here, times this whole thing, secant squared x times the natural log of the natural log of x plus, and then I guess I could maybe write that as tangent x over x, natural log x. And I suspect that the version, I'm not going to look in the back, actually I'm going to look in the back. Let's see if they have it written. I bet they have it written exactly like that. 29 from section 4.3. That times, they have these reversed, but otherwise it's identical to that. So in other words, there's no simplifying that you can do there. Number 37 is y equals tangent inverse of x cubed. So one of the things you just need to know is the derivative of a tangent inverse function, that's 1 over 1 plus x squared. But that's if this is just a regular old x, and so we have to apply some chain rule here. So the derivative of the tangent inverse of whatever is 1 over 1 plus whatever squared. And the whatever here is x cubed. So I think one of the common mistakes here is just putting an x there. It's not just an x here, it's whatever's in here, right? So it's 1 over 1 plus whatever squared, so x cubed squared. Sorry if I misspoke there a minute ago. That's the derivative of tangent inverse of whatever is 1 over 1 plus whatever squared. And in this case, the whatever is x cubed, times the derivative of what's inside, which is 3x squared. And a very small amount of simplifying there. If, for example, this was a multiple choice question, that's what the answer would look like. Number 39. Y equals the tangent of x to the negative 1. And the reason why this problem is here is to make sure we understand the difference between this notation and this. So here, this is not an inverse trig problem. That's why this problem's here, to make sure we understand that. The derivative of something to the negative 1 is negative something to the negative 2 times the derivative of what's inside. And that's it. You could try to simplify that a little bit if you want to, but not a huge amount to be gained there. So there's your answer there. So that problem could have been given to you in chapter 3, right? They're just trying to, our book, I think, and rightfully so, is trying to draw our attention to the fact that these are very different things, right? This means the tangent inverse function, and this is tangent of x upside down to the negative 1. All right. So from section 4.4, we're going to do 15, 19, and 27. We find that page. Number 15, we have, we're trying to evaluate what is the limit as x approaches positive infinity of the natural log, oops, sorry, wrong problem, of x to the 100 over e to the x. Okay, the first thing we need to check is what happens when you plug in infinity into this. Well, if you plug in infinity into this, you get infinity to the 100 power, that's infinity. And if you plug in what's e to the infinity, that's also some version of infinity. So this is an infinity over infinity. It's like a little thought bubble here. And that means this is a L'Hopitalable problem. And that's good news. That makes, if you have a limit and you can use L'Hopital's rule, that makes limits easier. So what L'Hopital's rule says is if you have something that starts off as an infinity over infinity or a 0 over 0, then you can use L'Hopital's rule. And L'Hopital's rule says that your limit is going to be exactly the same as the limit if you take the derivatives of the top and the bottom. Not quotient rule, just take the derivative of the top and the derivative of the bottom and then try again. So let's see, you take the derivative of the top and the derivative of the bottom, the derivative of e to the x is just e to the x. So let's try again. Now we plug in the infinity and we get infinity over infinity again. So I guess I can do L'Hopital's rule again. So that's 100 times 99 times x to the 98th over e to the x. And I should write in my limit as x approaches infinity, because I haven't done that yet. And I plug in infinity, and we get the same thing again. So this is like the 100 bottles on the wall. Take one down, pass it around, and then there's 99 bottles on the wall, and then that's a long song to sing, if you know that song. But what we need to recognize here is dot, dot, dot. If we keep doing this, what is eventually going to happen here and here? On the bottom, no matter how many times I take the derivative of e to the x, it's still e to the x. But on the top, if I keep taking the derivative of some number to a power, eventually, when I take, well, 100 derivatives of this, it's just going to be a number. So the derivative of x cubed is 3x squared, the derivative of that is 6x, and the derivative of that is just 6. So eventually here, I'm going to get 100 times 99 times 98, and it's going to keep going down 100 times 99 times all the way down, and by definition, that's actually the number 100 factorial. So it's eventually going to turn into that. And when I finally get here, and I plug in the infinity, this is just a number, albeit an incredibly huge number, divided by infinity. And a number divided by infinity is equal to 0. Doesn't matter how big that number is. If you have a number and you divide by infinity, that's going to be 0. So that's how that plays out there. And I certainly don't expect you to write out all the derivatives, like to keep going. You'd be expected to just understand that eventually, when you keep taking derivatives of x to the 100, eventually you're going to get a number. Number 19. So this, by the way, in our classification of L'Hopital problems, this is L'Hopital type 1, where you're starting off with something that's already in L'Hopital form. In this case, it was infinity over infinity. L'Hopitalable form is infinity over infinity or 0 over 0. Now number 19, the second example here I'm going to do for you is, let's see, the limit as x approaches infinity of x times e to the negative x. So right off the bat, that is not something over something. So this is clearly not 0 over 0 or infinity over infinity, at least not as it's written here. So let's see what's going on here. This is the same as, let's see, if I plug in the infinity, I've got infinity times e to the negative infinity. You got to think a little bit here about what e to the negative infinity means. E to the negative infinity means means 1 over e to the infinity. That's what negative exponents mean. And 1 over some number that's blowing up to infinity is 0. So this is like infinity times 0. So what do? To make this into a L'Hopitalable form, one of these things needs to be rewritten as the bottom of a fraction. And here, it's very clear what we should do here. Instead of writing e to the negative x, we could write that as e to the x on the bottom, because that's what a negative exponent means. And now, when I plug in infinity, I've got infinity over infinity. This is a L'Hopitalable form. So that means I can take the derivative of the top and the bottom. Derivative of x is 1. The derivative of e to the x is e to the x. And then I try again. So if I plug in infinity here, I've got 1 over infinity, and 1 over infinity is equal to 0. So that one was L'Hopital type 2, where we had to move one thing to the bottom, and then it became L'Hopital form. Number 27. Here the limit as x approaches 0 of e to the x plus x to the 1 over x. And this is L'Hopital type 3. If I plug 0 in here, I get e to the 0 plus 0. So e to any number to the 0 power is 1 plus 0. So that's like 1. And then 1 over 0. 1 over something that's approaching 0 is going to approach infinity. So this is an indeterminate form. If you're thinking, well, 1 to the anything power, that's just equal to 1, but something that's approaching 1 and the power is approaching infinity, this is indeterminate, just like 0 over 0 is. So what do we do here? So it's kind of like, I'd like you to make a connection between this kind of L'Hopital type 3 and logarithmic differentiation. So here, if I want to try to turn this into a L'Hopitalable form of 0 over 0 or infinity over infinity, then, well, before I do anything else, I'd like to take the natural log of this so I can get this to the outside. And to be able to do that, I need to make an equation out of this, because I can't just go taking the natural log of this, but I can do that if I make an equation out of it. And then take the natural log of both sides. So the natural log of the answer, L, this is the answer that I'm looking for, right? The limit of this is equal to something, I don't know what. So the natural log of that is equal to the natural log of the limit, and that natural log can move inside of this. So that limit here, if I take the natural log of this, I can use that logarithm rule that allows me to move the exponent to the outside. And that's worth pausing for a minute, making sure that you understand what just happened here. I took the natural log of this, and we have a natural log rule that says natural log of a number to the p power is equal to the natural log of that is p times the natural log of that number. When you studied logarithms, that was one of the rules. It's a big one for us. We use it a lot. This is one of the contexts in which we use that rule. So let's see what we can do here. Now that I've got that, one over x times that, so I can write that as the natural log of e to the x plus x over x. Now I should check to make sure that this worked and this turned it into a L'Hopitalable form. So on the bottom I have a 0 for sure, and then on the top I have the natural log of e to the 0, which is 1, plus 0. So this is a 1 here on the inside. The natural log of 1 is 0. So this has turned it into a 0 over 0 form, which means I can now do L'Hopital's rule. And Louboutins' rule says if you got a limit that's a 0 over 0, which this is, or infinity over infinity, then that's equal to the limit as x approaches 0 of the derivative of the top. So the derivative of natural log of whatever is 1 over whatever. And here, since that's not just an x, I have to use the chain rule. It's the derivative of what's inside. The derivative of what's inside is e to the x plus 1 divided by the derivative of the bottom. Again, this is not quotient rule. This is L'Hopital's rule. Just take the derivative of that, the derivative of that, and let's see what we get here. So natural log of L. Now when I plug in the 0, 1 over e to the x is 1 plus 0. So that's 1. This is equal to 1 over, times e to the x, e to the 0 is 1 plus 1 is 2 over 1. So that's equal to 2. So is the answer 2? Well, not quite. So that now we have the natural log of L is equal to 2. So the answer that I'm looking for, I actually would like to know what L is equal to, not the natural log of L. And the natural log of L, that means log base E. And by the definition of what a logarithm is, this means that L is equal to E squared. So the limit that I'm looking for is E squared. Those are, I think, maybe among the hardest problems in this whole chapter, L'Hopital type 3. But a little bit of practice, try a few of those, they're really not that bad. What you don't want is for a problem like this, I went through that kind of slowly because I was talking through all the steps, but a L'Hopital type 3 should take you maybe, like once you're practiced up, maybe 3 or 4 minutes. You just cruise through that, and if you can master those, you're in great shape.